All right, let's give this a try. There's an example where California license plates follow a specific pattern. They have a number, then 3 letters, then 3 numbers. So you can't have any zeros at the start, but zeros are okay in the last 3 numbers. You get no zeros as letters, and you can repeat the letters or numbers as much as you want. So how many different license plates can you do it this way? Well, let's start off by thinking about just the possibilities. Let's assume that you can repeat. So I'm just going to do a with repeat. And I'm going to take some notes here. Let's see, 1, 2, 3, 4, 5, 6. I'm allowed 7 different things. The first one has to be a number, but I can't use, let's see, I can use 0. No, I can't use 0, 1 through 9. So that's 9 possible things that I could have there. And then letters, and I can do 25 different letters. Is it 25? No, 26. No, 25 because no O's can be used because you don't want to get confused with those. And then for the numbers, I can use 9. No, it's got to be 10 because each number can be used. So just to make sure, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's 10 different things. Okay, so all I have to do is I have to multiply those together, and I get, let's see, fundamental counting principle says I get about 140,625,000. Okay, now I could consider about doing this without any repeats. Okay, you could see them saying, look, we don't want to have any repeated stuff. We want clear identifiers. And we can actually do this problem again. The first one, we can still have 9 different numbers, but then we can have 25 different letters to start off with, but then one of those has been used. I don't know which one, but it doesn't really matter. It just means there's 24 left. And then there's 23 left after that. Now, this one gets a little bit tricky. The number of possible answers on this new number is not 10, but 9. Okay, so think about it. I couldn't have used 0, but I've used one of the other ones. So I only have 9 left. And then 8 and then 7. See how that drops by 1 because I've been selecting. And this actually does affect our overall outcome. We only get 62,596,800 possible outcomes. And finally, let's see what could happen. Maybe this 0 thing isn't a big deal. Maybe you could just do any letter or number all the way through. So let's change the pattern. So any letter or number. Okay, we just want 7 placeholders all the way through there. So let's go with no zeros at the start. And how many possible outcomes? Well, we could have 9. Oh, wait, hold on. We get 26 letters. So 26 plus 9, that gets us 35, right? So it looks like I could get 35, 35, 35, 35, 35, all the way across. That's the number of possible outcomes I could have. And you'll want to check my answer on this, but I got 62. That's 62 billion possibilities. So with with a string of 7, we should be able to get pretty much anything that we need. So let's take a look at another one. I'm going to select 2 students at random to win a prize. It's going to get a grand prize and a second prize, but I've got a special rule in here. One of the girls in the class is going to win a grand prize, and one of the boys is going to win the second prize. Just look at the possible outcomes this way. Well, in this particular class, I'm going to go pretty simple in this. I'm going to define my sets to start off with. So my set of girls, I'm going to make it, let's do an A and let's do a J. And my set of boys, we'll go a little bit bigger on this. Now, those are the 2 sets. I've got girls, I've got boys. I've got 1, 2, 3, 4, 5, 6, 7, 8 kids in this class. So I'm going to represent this in a different way so we can see why the fundamental counting principle works as it does. On our first pick for the grand prize, I have 2 possible options. So this is the grand prize. So either A could win, or J could win. Those are my only two possible outcomes. If A wins the grand prize, there's another combination that could happen here. We could have, let's see, B could win, or C could win, or D could win, or E, or G, or S. And those are my possible outcomes. So looking at this, it means that I could have as my winning set, I could have A, B, I could have A, C, A, D. You sort of see the pattern here. So these are my possible sets that I could be creating. I guess technically they'd be subsets. And if we consider it this way, we can do the same thing if J wins. So J, we could have B win, we could have C win, D, E, G, or S. And then we would create the same kind of sets. Okay, and so on. So based on this representation, which is called a tree diagram, we can easily see why the fundamental counting principle works. If there's two options at the beginning, so two options for the first, and 1, 2, 3, 4, 5, 6 options for the second, counting all of these up, we discover we get 12 outcomes. Okay, and we can see exactly why that's happening with the branches. All right, I'm thinking of a 3-digit number. How many choices do I have? Well, a 3-digit number, there's 3 places, and I could have, let's see, there's 10 for each position. Wait, if it's a 3-digit number, I can't have it lead off with 0, right? That doesn't work. It has to be 1 through 9. Otherwise, it's not a 3-digit number. It's a 2-digit number that I stuck a 0 at the beginning. So then there's any of the other digits works. That tells me that I could have, that's 900 different outcomes for this. Okay, so that's a three-digit number. Now, some people could reinterpret this. They could say no repeats in the digits. And that's actually not as difficult a problem as you might think. The first one still has that rule of 9. After that, I can't repeat, which means that's going to be 9, because I could use 0, or I could use the 9 other number, or the 8 other numbers that are left over. And then I have 8 possible choices, so that's 9 squared times 8. I get 648 possibilities. So if you're looking for a 3-digit number that doesn't have any repeats, you have 648 possible, but just 3-digit numbers, you've got 900 possible 3-digit numbers. Let's imagine that I deal 5 cards from a deck. How many outcomes are there? Well, 5 cards. I'm going to do 5 slots. Let's see. We can do them close together. 1, 2, 3, 4, 5. So in a deck of cards, there's 52 overall cards. So the first card that I deal out, there's 52 possible options. And after that, let's see, there'll be 51, then 50, then 49, then 48. All we have to do, using the fundamental counting principle, is multiply it out, and I get this many possible hands dealt out 5 cards from a deck. Now, just to keep you on your toes, that means that the first card that I deal out, I could have 52 branches, right? And then from each one of those, I would have 51 branches coming off. And from each one of those, I would have 50 branches. Okay, so the fundamental counting principle uses this idea of the tree diagram, and it makes it easier to calculate with. I hope that helps out for 6-2, and I look forward to seeing your homework turned in.